Hey everyone, in this video I'm going to cover Chapter 8. Chapter 8 is all about the network layer. Let's take a look at 8.1 here. The network layer is towards the bottom of the OSI model, and really it's responsible for IP version 4 and IP version 6. Those protocols, I should say just IP4 is required to be on the internet. However, IPv6 can also be used out on the internet as well. The big thing with IP, when we talk about IP encapsulation, we have our data that we have broken up into smaller chunks, is we add a header onto it. That header is going to have our addresses, our source and destination IP addresses. I mentioned in a previous video that there should be no two IP addresses that are alike in the world. However, that's just a little bit of a misnomer because there is something called NAT here. What NAT does for us is it allows us to use the same IP addresses within internal networks. So for example, if I looked at my IP address, I have like a 192.168.1.10. And more than likely at your home, you're probably a 192.168.1 address as well. So I'm going to post a separate video in the shell that talks about NAT. But essentially what we need to know is that we need a unique IP address to deliver packets out on a network, and especially the internet. Because if we had two devices with the same IP address, we wouldn't really know where to deliver that to. We need to have a unique IP. And routers are responsible for getting the IP addresses to the correct destinations, or the data with the IP addresses to the correct destination. So again, with the network layer, one of the big things we're responsible for is for adding that IP header, which has our source and destination IP addresses. Now, characteristics of the IP protocol is that it's connectionless, it's best effort, and media independent. What that means is we do not establish a connection to the receiving device before we send. We simply just send it and we hope that it gets there. The analogy that they always give is, sending a letter in the mail. When you send a letter in the mail, you simply put your addresses on the letter, you put a stamp, you put it in the mailbox, and you send it. We don't know the path it takes to get there. We don't even know if it shows up in the mailbox. The only way that we know for sure that it got there is if we call up our friend or text them or something and say, hey, did you get that letter? And then they kind of manually acknowledge it. If you've ever tried to surf the internet, so you open up a browser tab and you type in the URL and it doesn't do anything. It just sits there and spins and spins and spins. And pretty soon you get page cannot be displayed. Then you hit refresh and boom, it all of a sudden shows up. That's IP at work because DNS, the DNS protocol, where it's trying to resolve that name to an IP, is using IP protocols. Connectionless, it's best effort. There's no guarantee that it's going to make it, so it relies on us to recover from the error. So the last part, that's kind of best effort that I just skipped past there because I mentioned that already, is it's media independent. So you can use the TCP/IP protocol whether you're going over copper, Ethernet, a wired connection, a serial connection, optical fiber, wireless. It does not matter. It's completely media independent. So the TCP/IP protocol is great for communication on the internet. Let's take a bigger look at the IP packet and the header. So if we take a look at the IP packet, down here is our actual data, but then we add all of these things. So again, that's called encapsulation. We have various bytes. We have the total length. We have source and destination IP address. We have the version, time to live, the protocol we're using. Is it DHCP? Is it HTTP? What is it? But you can see it's rather large. It's 20 bytes in size. There's a lot going on here. With IPv6, I'm going to skip forward to that here just real quick. With IPv6, it's a little bit more simple. It's larger, 40 bytes in size, and that is mainly because of the source and destination IP address length. These are 128 bits versus the 32 bits. So up in the header, there's not quite as much information. So it's a little bit more simplified. So we can actually send more raw data, I guess, inside of that IP packet. Now 8.2.2 gets into what all of these different packet fields are for. I'm not too worried that you guys know about it. Our main thing we need to know about is the source and destination IP address. Who are we coming from? Where are we going to? Those two addresses will not change. In 8.2.3, there is a sample video showing how to use Wireshark to view those IP headers. We've used Wireshark before. I would highly encourage you guys to check this out and do it. Gives you a better understanding of those IP version 4 and IP version 6 packet headers. All right, a little bit with IPv6. IPv4 is essentially done in terms of the address space that we have available. So there's approximately 4 billion IP version 4 addresses. But if you think about the amount of people there are in the world and how many devices each person has, you can see how we quickly depleted IP version 4. We developed a few things like NAT and private IP addressing to keep IP version 4 around. But really what that did is it gave us some potential problems. We have lack of end-to-end connectivity. We're reusing IP addresses, so to speak. It increased the complexity of our networks, and it's just really kind of a band-aid to keep IPv4 around. And I think IPv4 is not going anywhere, but IPv6 came on board because it gave us significantly more addresses. So instead of a 32-bit IP address, we now have a 128-bit address. So 4 times the amount of bits. Now what did that do? Instead of the 4 billion addresses we have available, we have 340 undecillion addresses. That is a lot. That's a bigger number than I can even comprehend. It's roughly equivalent to every grain of sand on the earth. I don't know how they calculate that, but that's what they say. The point is we are never going to run out of IP version 6 addresses. Now here's that comparison of the packet headers. Again, IP version 6 to IP version 4. You can see it's a little bit less cumbersome with IPv6. However, it's a little bit bigger because of the size of the addresses. With this page right here, 834, it gets into all the different things that we see in there. Again, the main thing for me is you know what the source and destination IP address is. And we'll get into what an IP version 4 address is and more specifics, and what an IP version 6 address is and how they look and how they work and how to do subnetting and all that to come. So get more in depth with that. The next section here is a sample video with IPv6 and Wireshark. Again, I highly encourage you guys to do that. Just gives you a better understanding. Now with the network layer, what we are responsible for is forwarding those packets to their destinations. We have to do host forwarding decisions. Mainly there's 2 devices that do that. It's our PC and then the routers. So what the PC has to do is the PC has to decide, is the computer I'm trying to communicate on my local network, so in this case PC1 to PC2 within the local network, or is it on a remote network? Now if it's on a local network, we can just simply communicate directly with that other PC. And actually on a local network, we use a MAC address because the switch looks at MAC addresses. But the IP address will still be there, and we'll look inside of that header when we get to PC2 to make sure, hey, this is intended for me. If it's on a remote network, then we have to use what's called the default gateway. Now what the default gateway does for us is it gets us to a router. So the default gateway is always an IP address of a router. And then that router can route to remote networks. So a host routing table looks similar to this. It's a little ugly to look at, but there's 2 main things we want to look at. We have this destination of all zeros. This is like a catch-all type of address. And what that says is send it to the gateway. And the gateway here is 192.168.10.1. And we get to that by sending out of the 10.10 address, which is our current IP address. If we want to send to the local network that we're on, 192.168.10 network, it's on our link, which means we just send it out of our current network connection, out of the network card that has 192.168.10.10. All the other stuff we won't worry about at this point, but we have this catch-all again, which says get it out to the gateway, and then we have this local network that we are a part of, which says, hey, it's on our link, send it out of our network card. Now, if we send it to a router, it's the router's job to try and deliver it. There's two, well, actually, I'll just stick with two. There's two decisions a router can make. The router can make a decision saying, hey, we don't have a route to that destination, and then we get a destination unreachable. Or yes, we do have a route to that destination, and we simply send it to the next router. So if I take a look at a routing table of a router, where is that at? Here we go. It looks similar to this. So this is router 1. Router 1 can deliver to the 10.110 network. It can deliver to the 192.168.10.0 network. And it can also deliver to the 209.165.200.224 network. Those are the only networks that it has direct connections for or specific routes to. How did those routes get in there? Well, as an administrator, we have to either manually put those routes in there, statically that's called. So we go into the router and we actually type in commands on how to get there. So here we do an IP route 10.110. So we're saying router 1, if you want to get to the 10.110 network, what you do is you send over to the 209.165.200.226 router. So router 1, if you want to get to that network, send to here. That's router 2, and then hopefully router 2 can then deliver it. Another opportunity we have as an administrator is set up a protocol called dynamic routing, where the routers just kind of simply share information back and forth, and then they learn about the remote networks and they learn about how to get there. A little bit beyond the scope of this class, that's more in the second networking class. But with the dynamic routing protocol, the routers build the routing tables themselves. Either way, the routing tables need to be built. The routes just don't automatically, magically get there. The packets don't just get routed around automatically. We have to do some sort of user intervention on our routers. So the routers need to be configured. One more route that this has, and this doesn't always have to have this, but it has this gateway of last resort. It's the static route with the star. And what this does is, hey, if I don't have a match for any of these down here, instead of dropping the packet and getting the destination unreachable, I will send it out of this connection, at least try to get it somewhere. So I don't have a specific match, but if you notice that quad 0, I have that catch-all again. And I can send it out, in this case, to the other router, and maybe the other router can get to the destination, maybe it can't. But at least we didn't drop the packet at this hop, as it's called. So that's it for this video with Chapter 8, relatively short here. There is a lot going on here, so I again highly recommend that you read the chapter in its entirety, but I just wanted to kind of focus on the main parts. Get out Wireshark, take a look at some of those IP packets, do some commands on your command prompt, such as ipconfig, and see if you can identify your default gateway, and you can see how that is on the same network as your PC. Try to give it a ping, see what type of results you get back. Maybe try to ping a remote network and do also a trace route to it and see if you can identify the hops along the way. Again, just kind of play around with it. Nothing required with these commands, just something you should start to be aware of as we go through the class. That's all. Thanks for watching.